Assalamualaikum warahmatullahi wabarakatuh. Okay, so our last topic, which is application of Laplace transform. So the topic will be referred from the James books. Okay. Okay. For the topics of application of Laplace transform, which is topic 8. So previously we have covered the solution of ordinary differential equations, which is this topic is the same as in 5.3 solutions in page 370 to 380, specifically in 5.3.3 ODE, okay, 372 and 377. So will not be discussed here. So you need to refer to the which is covered in topic 7. So what we'll discuss in these topics more on solution for differential equation system, which is state space representation, section 1.9, page 82. So in terms of single input, single output seesaw system, okay, multi-input, multi-output MIMO system, and solution of states space equation, section 5.7, page 450 for seesaw system and MIMO systems. Okay. So this is the previous topic that we have covered in chapter 7, which is solution in different equation. Okay. Okay. So this is what we'll cover in these topics. First is state space representation. Okay, the solution of differential equation initially value problems of order of n and can be reduced to the solutions of the set of n for the first order differential equation, which each will an initial condition. Okay, the single input, single output, or we call it as a seesaw systems. Okay, is the first set under consider of seesaw systems characterized by n order linear differential equation. So it's from the linear differential equation. So for example, an for dn over y over tn plus an minus 1, dn minus 1y, and dtn minus 1, and the rest equal to u. So where is your ai is a I in terms of coefficient of 0, 1, and n are the constant with a and should not be 0. And assume that the initial condition of y node, y1 nodes, and y node are unknown. Okay. So here, introduce the n variable of x in terms of t, which is xi, x1t, x2t, xnt lah. Okay. Then x1t is equal to yt. Okay. For x2t is a differentiation of yt, which is dy over dt. We call it as x dot 1t. Okay, x3t is differentiation, double differentiation of dy, so it's x dot 2t. Okay, so when you use dot, is dot 2 means that the double differentiation of dy d square y over dt square, and the rest. Okay, this is the formula. Okay, so if we substitute the 1.5, okay, this one. So we have something like this: an x dot n plus an minus 1 xn plus an minus 2 xn plus minus 1 and the rest n. So when we put as a xn as the main, the left side, so we get something like this. Okay, an minus 1 divided by an xn minus an minus 2 divided by an xn minus 1. So based on the represent of system and simulations, so what we can say that x dot 1 is equal to x2, x dot 2 equal to x3, and the rest, which is your xn is negative a naught divided by n x1 minus a1 divided by n x naught and the rest. Okay, so which can be written in the vector matrix differentiation. Okay, the vector matrix, which is on the left side will be your what we want to find, x dot 1, x dot 2, x dot 3, and the rest. So the matrix start with 0, 1, 0, dot, 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 or 0, 0. So the sec times the x1, x2, and the rest. Okay, this is the first for the x value. Okay, and then we have a ut value. So this is the matrix for ut. Okay, so where is x1, x2, and xn are and u are the function of t and restricted to the x1t, x2t, and the rest. Okay. So these equations may be written in terms of linear, which is x dot is equal to ax plus bu. Where is your x? T is a vector. We call it a state vector, and it contains all information that one need to know about the behavior of the systems. So the components have an n state of x1, x2, and the rest, which consider represent the coordinate of n dimension coordinate space, which is xt range. So this refer to the state space, okay, and as the time increases the x vector of xt, it will describe a locus of space called trajectory, and in two dimensions, the states reduced to phase plane. Okay, so we have previously matrix of A, which is called a system matrix, and particular of in 1.60, 1.60. So we have a matrix A here. Okay, so it's known as a companion form, which is adopted in practice. So in equation 1.61, it's referred to system state equations. 1.61a, this is a state equation. Okay. And the output response of the system determined in 1 by 1.59 is determined by y, which is determined by x1. So y equal to 1, 0, 0 times x1. Or we can see that y is equal to transpose of c of x. So this is the transpose of c, which is this one. Okay. So you have a two formula here. So a distinct the advantage of vector matrix approach is that the application is multi-variable, that is a multi-input, multi-output system, and deal in the next section. So in this case, it is particularly important to distinguish between the system state variable and the system output, which is generally a linear combination of the states. So together, the equation of 1.6a and b, we can see that x dot equal to ax times bu, and y equal to c transpose of x, so which is a dynamic equation and are commonly referred as a state space model representation of systems. So this is called as a modern approach to the analysis of design control system. So we use this most on the control system engineering. So it's an advantage in adopting a vector matrix representation of 1.6 in compact of notations. So the final general equation that mostly we use is the linear combination of both, which is x dot equal to ax plus bu, and y equal to c transpose x and du. Okay, so we go. Okay, this is the simplifications. So for the transpose, we have something like this. A n minus 1 divided by a n minus a minus 1 divided by n, and the matrix. So B is 1 over n and 0, 0, and C is a 0, 0, 1. Okay, we go for example. Obtain state space representation of the system of the third order differentiation. So when you get this type of question, you have a d power of 3, okay, 3d dy dt power of 2, okay, differentiation of 2, 2 dy dt for n, for x, and the function of exponent t. Okay, so we know here is x1, we can y as a x1. So x1 is a y. Okay, so x2 automatically is a differentiation of y. So dy over dt. So it's a, we call it as a dot 1. Okay, then the third one, you have x3 equal to the double differentiation y over dt square. So we call it as a dot 2. Okay, so you have these three main term. So what we need to do next, we know that we need to find the x dot 3. Okay, x dot 3. So which is, we know that x dot 3 is equal to the third differentiation. Okay, so here we have a third differentiation. So we can simplify this equation to be, make it this x dot 3. So make it everything on the right side. So what we'll get, we get something like this, which is x dot 3 okay, x dot 3, okay, is equal to d3 over dy of dt, and put this everything on the right side. So you will get negative, so you get something like this. Okay, same like the previous one, dy of t is this one 4y become positive 4 1. Okay, so this one negative dy over dt, when we bring to the right side become negative dy over 2 dy over dt, positive of dy over dt, on the right side will be negative dy over dt, and plus the exponent for t. If we simplify it, we can know that y equal to x1, so automatically we can go for x dot 3 is equal to 4x1, okay, minus 2 dy over dt, we know x2, so we put it x2 minus 3, double differentiation of dy over dt is x3, so we put it x3, and plus exponent t. So we have this equation of x dot 3. Okay, so now what we need to do, from this equation we change to the matrix form. Okay, so the left side is will be x dot 1, x dot 2, and x dot 3. This is the main matrix that we want to find. Okay, the second one is the equations. So it's a 0, okay, based on the previous equations. Based on here is 0, 1, 0, 0, 0, 1, and the rest. Here will be 0, 1, 0, 0, 1, 0, okay, 0, 0, 1. And the final one for x3, we have this equation. So we know this equation x3, x dot 3 is 4x1 and the rest. So that will be, you are just putting the 4, negative 2, negative 3. Okay, this is your function of x1, x2, and x3. Okay, plus in your equation you have exponent t. So you put it there in metric form 0, 0, 1 to the exponent of negative t. Okay, so you have the first matrix. Then from here, we know that our y, okay, y equal to x1. So the matrix will be y equal to x1. So in terms of matrix, the matrix will be 1, 0, 0 of the x1, x2, and x3. So we know 1 times x1 become x1. This 0 times x2 becomes 0 and 0. So they'll get y equal to x1. So this is the two main equation to constitute the system state space representation of the system. Okay, so we now proceed to consideration of the general of seesaw. Okay, one input on output systems. So this is the formula of differentiation. Okay, in which the input involves derivative of term. Okay, there is a various way of representing 1.66 in the states of the form depending on the choice of the states. And illustration, we shall consider only possible approach introducing of exercise. So we define as 1.6 that A we take about this formula, and B is 0.01 transpose, and C is the transpose of this one. Okay, so next we go for the next example. Obtain the state space model for the system of the differential equations model. So you have x power of 3, okay, x power of 2, 1, dy dx, then this is in terms of u. Okay, so these equations, automatically we know that x power of 3 is similar like previously. X power of 3 which is x dot 3. This one will be x dot 2, this one will be x dot 3. So you can make this equation. So become x dot 3 is equal to, bring everything to the right side. So you will get negative, okay, negative 6, okay, d square over dy, d square minus 11 dy over dt minus 3y plus 5 du over d square u over dt square plus du over dt and plus u. So this is your y equations, the third equations. Okay, this is your equations. So we can simplify this equation to be x dot 3 is equal to negative, okay, dy over d2. If you see this example, dy over d2 will be x3, okay, under x3. So dy over dx is 1, x1 will be y. So this one, okay, will be dy over d2 will be dy over d2 will be x3. This will be x1, x1 will be y. So this equation will be negative 6. Okay, dy over d2 will be x. Okay, we start with x1 first. Sorry. Okay, we take x1. So we know that x1 will be y, x2 will be dy over dt, x3 will be d square y over dt square, and okay, so normally until x3 lah. So the equation will be y, this is the 3y, 3y will be negative 3x1, okay, minus 11x2 minus 6x3 and the rest lah, okay, plus 5, okay, du over dt and the rest. Okay, from here, so this the first x equation we can put in terms of the equation of matrix. Okay, so where is, okay, we know that your x1, the matrix will be 0 1 0 0 0 1, then the x3 will be based on here. So negative 3, negative 11 and negative 6. Okay, in terms of b is 0 0 of 1. Okay, so your c will be focusing on the du over the u term. Okay, the u term will be focused on the c, which is u is 1 1, du over dt will be 1 and d square over dt will be 5. So it's a c transpose. So the space equation will be x dot ax b du equal to, another one is y equal to c transpose of x. So you can see ax is based on the main equation, okay, okay, from here, and also the third x1 will be x1, x2 and x3 n. So you will need to use the x3 of this equation. X1 will be the first equation will have x1, x2, okay, then the last equation will be this, something like this. So for B is 0 0 1 transpose, okay, so this one will be based on u. You have one u here, so automatically 0 0 1 times u. So you get this one. And your y is based on here, okay, is 1 1 t, which is a transpose. So you will get a y equal to transpose, where is your c transpose is something like this. Okay. So this is a block diagrams. Okay, next is a state space representation for the multi-input, multi-output system or MIMO system. So many practical systems are multi-variable in nature, being characterized by having more than one input and more than one output. So in general, the state space model is similar to the 1.63 for the CISO, the previously, and except the input is now a vector and the output is now in y term, yt term. So thus, more general form of corresponding from 1.63 of this states represent of n multi-input, multi-output MIMO in R input and L output. So your x dot will be ax plus b bigger bu, and you have y equal to cx plus du. So a additional of du. Okay, so this is the main equation. So where is your x is a vector? Okay, x is a vector, u is the r output vector, okay, u is r output vector, y is the l output vector, okay, y is l output vector, a is the matrix just now, b is the nr control input, and c and d respective for l times n and l times r. Okay, so this is an example. Obtain the state space model representation characteristic of two input, one output parallel of the networks. So this is the networks, okay, in this figure. So you need to obtain the function of this one and this one. Okay, so where is your element x1, x2, x3, and x, u1, u2 are indicated in figure. Then the output of y is voltage drop across the L1 indicator, which VC denote a voltage drop of the capacitor. So in order to solve this one, you need to use the second law of Kirchhoff. So you have the first equation, which is R1 I1 plus L1 D1 dt plus VC plus exponent 1. This is your first equation. You have second equation L2 di2 over dt plus VC plus E2 with the second equation. The third equation will be the voltage drop, which is your V dot C equal to 1 over C I plus I2. So you have three equations. And the output being voltage drops is indicated by L1, which is Y equal to L1 D1 over dt. So you have a four equations here. Okay, this is the output, two input. Okay, two input, and you have a output here. Okay, what you need to do now first, when you have this one, you need to change in term of y. Okay, we know that y equal to L1 d1 over dt, so this one can change into the y. So automatically you get the formula will come y is equal to negative ri R1 I1 minus VC plus exponent 1. This is your first, the third equation. So you get this one. Okay. So that's why we get this one. Okay. When writing, for example, x1 is equal to I1, x2 equal to I2, x3 equal to VC, ui equal to x E1, and u2 equal to x. So the formula will be, from here we change everything into these terms. So you will get, for example, R1 L1. So we know that 1 become x1. So you will get something like this. If R1 x1, okay, plus L1, okay, okay, d1 dt, okay, what d1 dt equal to y bc exponent 1 dt you change this one for x1, so this one will be y, okay, vc, we know vc is x3, okay, x3, and plus equal to exponent 1 will be u1. Okay, Okay. Okay, again, so what happened is we have three equations. The first equation, this one, okay. So second equation and the third equations. So we know that y equal to L1 over d1 over dt. Okay. So whereas we know that, okay, di over dt is equal to x dot 1, d square I over dt square is equal to x dot 2, and d 3I over dt third equal to x dot 3. So from here, we change each of the equation in terms of x1. This is what we want to find. Okay, the first equation will be, okay, we know that y is equal to just now L1 di over dt. So di over dt is equal to x1 dot. So what we need to do is from this equation, we make y, okay, sorry, this is not x1, x2, and x3 lah. Okay, so what happened here, so your main equation here, so the first equation will be y equal to negative ri, r1i minus bc plus exponent I. So this one we can simplify. We know that L di over dt is equal to negative r, okay, we put it x1, I1 equal to x1, so negative r x1 minus bc is equal to x3, okay, plus exponent 1 become plus u1, 1. So when this is L1, so for x1, okay, d1 over dt, x1, this was, we change this one to x1 is equal to, everything will be divided by L, which is negative r x1 L1 minus x3 L3, sorry, L1 divided by L1, plus UI, U1 and 1. This is your first equation. So we go for second equation. So we know the second equation will only remain L2 D1 D2 VC. So the equation will be di2 over dt. So the 2 1 in number 2 will be negative. Put everything on the side will be negative VC plus E2. Negative VC plus E2, okay, divided by L1, L2 lah. So this one can be simplified. VC will be x3, the negative x3 over L2 plus U2 over L2. So this is equation number 2. The third equation will be this one. VC1 over C, Y1 plus this one. So we get a VC equal to 1 over C, which is okay, I1 plus I2, or we can simplify, okay, 1 over C. What is I1? I1 is x1 and plus x2. So we have a 3 equation here. So we can put everything in the matrix form. Okay. So we go for the first equations. So x dot 1, okay. Okay, in terms of the matrix, the first column will be negative R over L1, R over L1. X2 is 0, so that's why it becomes 0 here. Okay. Then x3 will be 1 over L1, so become negative 1 over L1. So that's why you get negative R over L1, 0, negative 1 over L1. So this one will time this one, we will have a x1, this one will x2, it will be 0. This one will times this one will be 0. Then, okay, we go for x first. We go for x first. Focus on x first. This is equation number 1. Equation number 2, you only remain x3 and x3 only. Okay, so that's what 0, 0, 0 times x1, 0. 0 times x2 0. So you remain negative 1 over L2. So you will get this one. And the third will be focusing on x1 and x2. So 1 over c times x1, 1 over c times x2, you get this one. But x3 will be 0, 0 times x2. So you solve the first x equation. Okay, this is the x equation. Now plus, this is the u equation. So in this case, the first equation, you have ui times li. So that's why 1 over li times 0. So you have a two constants, which is u1 and u2. So that's why the matrix will be 2 times 3 times 2 times 1. Okay, so the second equation, you have u2 L2. So that's why 0 times 1 over L2. Okay. The third equation, there is no u, that's why 0, 0. So this is the matrix of the equations. Okay. So next, in terms of y. So we have this y equation based on this equation. Okay. So the y equal to negative r, okay, x, this one is x1 minus x2 will be 0. So see, almost similar like the first equation, 0. Okay, that's why it becomes 0. So the third one, you will have negative vc. Vc here is x3, similar like this one, x3. Okay, but this one there is no over L. So we focus on y. So we negative 1 times x1, x2, x3. Then you have a uil1. So which is your metric will be 1, 0. ui u2, u2 is 0, u1 is 1. So you will have this for y equation. This is one trait for a and also b. So automatically your requirement x dot, okay, the form function of x dot is equal to ax plus bu. Where is your a is this one, matrix of a, and b is this one, matrix of b. Okay, then the second vector is y is equal to c transpose x plus dt transpose u. Where is your ct transpose will be this equation. Okay, and also dt is this equation. So this is how to solve the state space representation for MIMOS. So just now, CISO and MIMOS. Okay, thank you for the first section.